Good evening, good morning and good afternoon. A very warm welcome to our first plenary session. This session is a very special session. This contains a special lecture called First I.I.Sc. Samshir Prakash Distinguished Lecture, which will be given by Professor Stokoi. Formal introduction will be given by our chair and co-chairs, and the other lecture would be given by Professor Adrian. And we are very thankful to both of them. This is a really odd time for our distinguished speakers, but they kindly accepted and delivering lectures. Before I hand over my session to Professor S.K. Prasad, who will be the chair of today's plenary session, I would like to briefly introduce about him. He is a well-known personality in India as well as abroad. He has vast experience. For the sake of convention, I'm just briefing. Dr. S.K. Prasad is the professor and head of Department of Civil Engineering at Vidya Vardhaka College of Engineering, Mysuru. He is having over 35 years of teaching and research experience. He obtained his bachelor degree in civil engineering from the University of Mysuru, securing first rank in 1982. Master degree in Geotechnical Engineering from Indian Institute of Technology, Kanpur in 1985, and doctoral degree from University of Tokyo in Japan in 1996. He was a visiting assistant professor at Asian Institute of Technology, Thailand for January 2006 term. He has published over 160 technical papers in national and international journals and conferences, guided over 70 master dissertations, and guided 3 doctoral students. He has completed several sponsored research projects from JSS MFE, AICTE, and DST. His areas of research interest are in earthquake geotechnical engineering and in performance-based design.
Thank you, Professor Jekka.
Thank you, sir. I will introduce our co-chair, then I will hand over to you, sir. This session will be co-chaired by Dr. Indrajit Pal, I.I.T. Thailand. Dr. Indrajit Pal is assistant professor and chair in disaster preparedness, mitigation and management, Asian Institute of Technology, Thailand. Dr. Paul, having more than 18 years of experience on research, teaching, training, advocacy, consultancy, primarily focused on disaster risk governance, hazard and risk assessment, risk perceptions, participatory DRM, public health risk, GIS, and remote sensing in DRM and climate change adaptation. Dr. Paul has published number of books and research articles in referred journal, national and international journals. Dr. Paul is member of Board of Directors for the Global Alliance of Disaster Research Institute, Japan. With this brief introduction, I request Professor S.K. Prasad and Dr. Indrajit Pal to take over the session and continue. Thank you, sir.
Thank you very much, Professor Jekka.
Thank you.
I'm extremely happy that the 2 speakers, Professor Stoko and Professor Roderick Marek, are here. I'm also very happy to have Dr. Indrajit Pal here. Please, Dr. Indrajit Pal, give me opportunity to introduce Professor Stoko, and I request you to summarize at the end. Okay. Well, good. Let me take pleasure of introducing Professor Stoko. Good morning, or should I say good early morning, to delegates from America and Europe. Good evening to the delegates from South Asia. And good late evening to the delegates from East Asia and Australia. It's an honor for me and to my colleague Professor Indrajit Pal to chair the first plenary session of the 7th International Conference on recent advances in geotechnical earthquake engineering and soil dynamics. We are sincerely thankful to the organizers of the conference for the opportunity provided to us. We all know that earthquake geotechnical engineering has evolved over the last 6 decades tremendously. The understanding of wave propagation through the soil has always been a serious challenge, even today, considering the complexities in soil, heterogeneity, inhomogeneity, nonlinear behavior, pressure level dependency, strain level dependency, strain rate dependency of soil, and the randomness of earthquake wave are among a few of the complexities which make the assessment of vibration at ground surface very challenging. If at all, we have achieved some understanding in this direction, the contributions of Professor Kenneth Stocko are considerable. I'm proud to present Professor Kenneth Stocko from University of Texas at Austin to the delegates of 7ICRAGEE. Professor Stocko does not require any introduction. However, for the sake of completeness, I wish to briefly introduce him. Professor Kenneth Stocko has been working in the area of field seismic measurements, dynamic laboratory measurements, and dynamic soil structure interaction for more than 40 years. He has been instrumental in developing several small strain field methods for in situ shear wave velocity measurements. He has also developed 2 types of resonant column systems that are used to evaluate dynamic soil properties, dynamic rock properties in the laboratory. Over the last 14 years, Professor Stocko has led the development of large-scale mobile field equipment for the dynamic loading of geotechnical systems, foundations, and structures, an activity that's been funded by National Science Foundation in the NEES program. NEES stands for Network for Earthquake Engineering Simulation. The equipment has already led to the development of new testing methods to evaluate soil nonlinearity and liquefaction directly in the field. Professor Stocko has received several honors and awards, including election to the National Academy of Engineering, the Harold Money Award from the Society of Exploration Geophysicists, the Eugen Togler Award from American Society of Testing and Materials, and Bolton Seed Medal, and the Carl Terzaghi Distinguished Lecturer from the American Society of Civil Engineering. That the title of his talk today is The Increasing Role of Surface Wave Measurements in Site Characterization. I'm also very pleased to mention that this lecture is the first ISET Shamsher Prakash Distinguished Lecture. Sir, you have 40 minutes time. I'll remind you 3 minutes before. The platform is yours now. Please go ahead, sir.
Thank you very much for that very kind introduction. It is basically 1 a.m. in the morning my time here in Hawaii. So I'm wearing a Hawaiian shirt, no tie, but I am happy to have 2 grandsons with me who are making sure that everything runs smoothly. But we're having a good time here. However, I very much look forward to giving this lecture, and I hope there are some interesting points that I can convey to everybody. Okay, this brief outline. Look at body and surface waves for field seismic measurements of shear wave velocity, overview surface wave measurements using, the SASW method, spectral analysis of surface waves, one that we use a lot. Present a number of examples that will hopefully give you some ideas and some concluding remarks. One other thing I just would say quickly, the National Science Foundation from the United States is happy to work with other countries. We've been in New Zealand for one, and help develop other people's capabilities with this type of equipment. So if you send me an email or something like that, I don't want to be inundated, but there's we would be very happy to interact with you on developing such type of equipment. You can see if it's worthwhile to you. Okay, and a couple concluding remarks there. Okay, just talk about field seismic methods, and I want to make one very important point. So the cross hole, 30 years ago, it was used a lot because it's a very fine measurement technique. The waves stay more or less, you know, most of the time we have horizontally layers or slightly inclined. So the waves are in there, and something happens that you don't realize that's the benefit. So when you use initial arrivals is what they do, and as you see the spacing is only 10 feet, 3 meters between boreholes. But you use the right frequency content, giving the right wavelength that works properly for the measurement, okay, with a good impact. When you start talking about downhole methods, now things get a little more complicated. It can be traditional, seismic CPT, seismic DMT, dilatometer measurements. But now if you start going into the waveform, you're going to get a waveform that's much too long for the layers you feel you're identifying, and you will not get correct numbers. PS suspension logger, so when we come down here to this one, you can see that it's 1 meter spacing between sensors, and that's where they're measuring. You need to use very high frequency. I'm not sure that's always done, but it is used a lot in the United States these days for maybe drilling one deep hole and logging that. And finally, the thrust of my talk is surface waves. And I'm an active source guy with all the big equipment, but passive sources are also used and work very well. But we can do some very deep testing with active sources. And they can even go deeper with passive sources at times. But in all of these techniques, wavelength is an important factor. And in the body wave measurements, 1, 2, and 3, wavelengths are typically ignored. Not good. And I'll show you why, but using surface waves. Okay. Just the other thing is, when you start looking at this, you start looking at the material that's sampled. So let's just say that this is a borehole right here, the vertical one right in the center, up and down. You can see where the downhole, it'd be like 2 or 3 meters away. And it's this zone that you're looking at going along that borehole. If you look at the PS logger, it's between those two horizontal blue lines where the cursor is going around right now, where they make a measurement. So it's a really, really fine resolution measurement, but now how it translates to earthquakes and earthquake responses is sometimes of concern. And finally, surface waves, and I'm just going to show you 2 different spacings because it's between receivers that we make measurements. So here, this 15-meter spacing will basically, and you'll see why in a little bit, give you this zone down there that you have sampled well. The 30-meter one is going to give you this zone down here, sorry, with the longer dashed black lines. And you build basically a pyramid that's up near the surface and then gets wider the further you go. But if you worry about lateral variability, you'll see that we use surface waves, shallow measurements, and maybe multiple points. Okay, next. So here's the overview of surface wave measurements using SASW, and you see down there in the bottom of the slide, the spectral analysis of surface waves. And whenever I talk about surface waves, I'm talking about Rayleigh type waves. Some folks will use love waves. We don't see them used that much in engineering, much more in geophysics. But we're going to talk about Rayleigh waves. And the key to a Rayleigh wave measurement is the keys. You need a good source that generates the frequencies, hence the wavelengths that you're trying to measure. And you need calibrated, well-acting receivers. And a 1 Hz geophone, by the way, I'm sorry, I'm going to talk in terms of Fahrenheit. but I've never seen anybody say these sort of things, but we've learned it the hard way. When those geophones that have big springs in them and so forth get to be above 90 degrees, really 92 to 93 degrees Fahrenheit, sorry, they begin to warp and they lose their calibration. We even have ice packs that go over them, little coats that go over them in the desert when we're out there in very high temperatures. Okay, that's an aside, but just to keep you alert. So the surface wave method is based on surface waves, Rayleigh waves, and they have the strain distribution that looks like this. Okay, and so basically that would be one wavelength, and you'll see it here again shown on the surface in a minute. But it's mainly this part of it, about the upper half of the wavelength, that really samples the material and gives you a good measurement. So you need to make this wavelength would see the upper part of layer 1. This wavelength right here would see the lower part, the upper and lower part of 1, maybe a little bit of 2, but you're going to build with longer and longer wavelengths, deeper and deeper that you sense. And that's the whole idea. And so you're your forward modeling is going to be taking out the surface layers that you have measured and know the velocities, and then continuing on to deeper layers where you are able to evaluate those velocities with longer and longer waves. Okay, here we go. And this is showing that dispersion measurement. So we have a site over here, 3 layers, velocity increasing with depth. This first wavelength, higher frequency, is going to generate a phase velocity through that material that's here. This next one, and there are going to be hundreds of these, but the next one is going to go lower, so it's going to see this surface layer and some of the lower layer. The lower layer is increasing velocity, so the overall phase velocity that moves with is going to be higher. And the idea in the field is to get this wavelength versus phase velocity, and it's going to be wavelength versus frequency in the field curve, and it's a dispersion curve. This is a normally dispersive. That means everything is increases. With depth, we don't have inversions and so forth, just to make a simple case. All right, so, and the testing we do, we use a common midpoint. And that common midpoint or center line is shown right here in the white. And we would place a receiver there. That's a middle receiver. You're always working in receiver pairs because you're determining the phase shift between the 2 receiver pairs. So here's receiver 1 and receiver 2. They are spaced at a distance X. The source is over here, and it's also spaced at a distance X from the first receiver. Then you see the second receiver pair, R2 and R3, and those are 2X. So this is for the shallower part, this is for the deeper part of collection at that array, but you can see that for the second pair, the source to the first receiver in the second pair is 2X. So you're always keeping the distance from the source to the near receiver in the receiver pair equal to the distance between the receivers, 90% of the time at least. But that's a general testing approach. This would show, you know, you're just starting here with short spacings. And let me go backwards, excuse me, because one thing I didn't mention is you can have an impact source, you can have a random noise generator, you can have step sinusoidal vibration. I'll show you all 3 of those. Okay, so we have our center line, we have short spacings, we then, the biggest spacing there is 2X, then we'd make this 4X here and 8X and so forth, and you just get larger and larger spacings. You're going deeper and deeper until you run out of energy, until you can no longer generate energy that will propagate that far. It all depends. I mean, okay. Here we're now looking also in the last 4 or 5 years, lateral variations. So this is just a special arrangement. It is very nice for us where, okay, we start out with the short spacings, and then after some distance, we have, so here, this would be the last of the short spacings, it's 2x. Now here it's doubled, so we're going deeper. Here's 4x. Here's 4x there between those two receiver spacings. Here is our normal R2 and R3, that's 8x, but we add a fourth receiver, so that's 4x and 4x. I'm talking about the spacings between the receivers. So now we have three zones, three vertical planes that we're looking at, and we can see how the dispersion, each one of those planes is the same or different. And that's the way we look at lateral variability, sloping ground, and things like that. So it's always changing. People are always making improvements in this. Okay, active sources. On soil, when you first start, so here we are in A, there's a sledgehammer that the guy's just hitting down. That's an impact source, got lots of frequencies. Receiver 1, receiver 2, receiver 3, like we had in the simple array, 1 hertz geophones. If that was on concrete, they'd be accelerometers, and it would be shorter spacings. But we're mainly talking soil now. So if we want a random wave generator, a bulldozer moving back and forth is an excellent random wave generator. Random wave collection is very fast, so is impact collection. But, you know, here would be your two receivers, and then the source would be coming within X of the first one, and it'd be going back and forth, back and forth. Sometimes the bulldozer drivers get a little angry with you because they're working very hard, or the machines are working very hard. But it's an excellent source, and I'll just show you various projects where we've used it a lot. Then this is our piece of resistance. There's one of these in the world. We call it liquidator. It's a step sinusoidal vibrations, and when you do it, you come from high frequencies to low, and you see over here, that's the start, high frequencies, that's the taper, that's a little exaggerated. High frequencies are getting lower and lower, and down here you'll see that gives you various facts about spacings and so forth. But we typically, whatever the spacing is, we typically have like 100 frequency steps in the spacing. And the longest spacing, let's say the longest spacing was 1,000 feet, 300 meters. That might take a half hour of that machine just turning away to generate all the energy to give you a good record. Okay, so here we go. We're going to look at liquidator used as a source. And this is real data. The sketch above just shows what we have, but this is real data from a nice site, of course. And what you see here is up here is a wave that is exactly one cycle from the source to the first receiver and one cycle from the first to the second. And this is wrapped phase so that you can see it in the field easily. And what you see, okay, we haven't got any energy here because the normal operation of the liquidator only goes to 1 hertz. And so we start here, but we have to know that's coming back to 0. So we have to collect enough data for that. So here's going to 100, a minus 180 degrees. That really would look best going vertically as a dashed line, because that 180 and the 180 below are the same. And so now you have 180, that's 360 degrees. That's A. The point A is the A wave right above it. That's one wavelength. Then this is half of that wavelength. That's a third. That's a quarter. So you are performing QA measurements in the field. While you're doing it, making sure you're collecting good data that's proper for normal analyses. And for point A here, you see the phase velocity, frequency, turns out the frequency is 4.37 hertz. The wavelength, because we know the distance between the receivers, we can be calculating this in the field, huh? And that there is 180. And so the velocity there is 790 meters per second. Okay, I'm going to show you B and C. B is the blue line up here. It's 2 cycles. So there you see 2 cycles. C has got 4 cycles. There's C in that one. And again, and I like this very much, and I'm going to stress it, I'm sorry, because we do NQA1 work a lot, nuclear quality assurance level 1, and it's all kinds of calibrations and things. But you are performing quality assurance of your data in the field when you gather it, and you don't walk away knowing, you either got it or you didn't, and if you didn't, you got to figure out what other things you have to change to get it. So it's extremely helpful. All right. I showed you A, B, and C. This is a phase plot now. So you see a phase plot vertically, phase velocity, and wavelength on the log scale, because you're going to cover so many such a wide range in wavelengths, 10 times what we get in velocity. But that's curve A, that's curve A from the record you saw, point A, point B, and point C. So here we go. I have graduate students, so it may look like a lot of work to color code all these spacings, and it is, but there they are. So all of that's going from very short, less than 2 meters. There's point A, by the way, where it fits in everything that we've got, to the longest wavelength we have here, which is 860 meters. So we would say we've got good data to 430 meters. And we did this in half a day, and all from the surface. You can't get cheaper than that, I can tell you, for that kind of depth investigation. Adrian would even agree with at least half of what I said. I'm not sure all, but that's okay. We're good friends. I see him there, and he's a good fellow. Okay, so here we now do best match and forward modeling. We like to use our head a lot of the time because it can be quite complex. And the match gives us, the match gives us this shear wave velocity profile that you see at the site. And as I said, here we're going to 430 meters, and we did that in half a day. Okay, so that's the basis for the testing technique. By the way, we also are doing, and I shouldn't really say this, spectral analysis of body waves, because you can do a lot of things with body waves and looking at wavelengths too that are very interesting. And you can invite me back at another time and I'll give you more of that. And we're heading towards in situ material damping, and you can identify material type much better with material damping than with material stiffness. So there's still a lot to be done out there, a tremendous amount. Okay, I'm going to give you 4 examples, and do you see them there? That's okay. I won't waste time talking about it. Here's the first thing, Dillon Dam. We needed to know the quality of the alluvium within and beneath this embankment dam. It's in Colorado. That reservoir is one of the best Denver has, the city of Denver, that supplies water to it. But it was going through a reevaluation for earthquake response. And that's why, and it hadn't been done before, and that's why we got involved. And so it's really looking at the general approach of estimating the quality of the material. And here we go. That means we have a reference where, oh, this is good material, that green dashed line. And wow, we measured in the field this, oh, that's great material. Uh-oh, we got a problem here because this is below the good material. And so we got to figure out what to do with that. But below that, we're in good shape. Absolutely, you see things like that. Here's another one. That would be like the dam, for instance. Here's another one that you might look familiar to you. Here's before, and then here's dynamic compaction, dropping the big weight to the Menard approach. And there's the improved zone and how much it improved and so forth. Okay, so here's back to the dam. This is the dam, Crest Road, and we're looking at the downstream face, but only partially up it, and the tow road and the downstream area. So I'll show you some data there. This is saying the same thing, but in cross section. So downstream, we're looking at the natural alluvium. We won't worry about the bedrock. You'll see a fence here, and now that's along the toll road, and right at the toe of the downstream face, and then several in the downstream face. Okay, here we are. Here's the dam right here. If you notice, there's a little road. It looks like that road was built so that this drill rig could go up there and drill. And I can tell you, they got almost nothing out of the drill rig, and you'll see why in just a moment. There's our good random source generator. We only had to go down like 50 meters. It works like a charm. And here's where one of the areas where a test pit was developed, and I'm going to show you the test pit. So here's the test pit in that case. And you can see large material. That's Professor Ed Idris digging. I have never seen him do that before, but I asked him to pose doing that for me taking the picture. Don't tell him I said that, Adrian. And here is Dr. Gonzalo Castro, two very fine people that were involved. And this just shows you a general gradation curve. And they tried to sieve it before they put it in the dam. So that's for the natural material, but the material in the dam had that vertical cutoff. So within the upstream and downstream shells, you see on that red line right there, and it's basically half cobbles. And then you get into a lot of gravel and just not that many fines. Okay, so it's a very interesting material. Here are we like to show it this way. Here's a number of profiles that we did in a particular, in the bulk of the area, but not all of them. Here are the profiles by the gray lines, and then here's the COV. In this case, they wanted the mean, not the median, because we normally plot the median. But here's the mean and the plus and minus 64th percentile, and looking at this remarkably low number, 0.1 in a natural material is very, very unusual. And I'll point it out again in another example. But we got very good profiles. The last thing I should tell you is right near the surface, they didn't know what because it's downstream, for the natural alluvium, they didn't know what the contractor did, and there was quite a bit of variability. So the top couple meters was thrown out, and they didn't worry about them. Okay, and what we'll do is we're going to take, well, this shows you, before I was ahead of myself there, this shows you the natural alluvium is in the gray dashed line. The alluvium in the dam and below is shown in the yellow, and here's the dam material. So here's the yellow, that's dam material. And then this is natural in yellow, the natural alluvium beneath the dam. And you see the natural alluvium off to the side. Now, when we take a look at this, we see that here is 3,000 meters per second. So this stuff is basically very stiff, hence it's dense. The compacted alluvium in the dam is similar to the natural alluvium, so it's dense and not cemented. I'll prove that to you in a minute. And there's no loose zone in the alluvium under the toe of the dam that they were worried about. Okay, now, what am I going to prove to you? And you're sort of covering up some of my words, so I hope I get them all right. But this is okay with the pictures. Divided it into 3 groups, not a big deal, just different areas, and we have more than that. But we plotted them like a resonant column test. That means log of shear wave velocity versus log of confining pressure, but now expressed as vertical effective stress, okay? And what you see is natural variability in the wiggles in that, but you see a line drawn through all of that, which says the VS1, so at 1 atmosphere, is 1,245 meters per second. And to go up and down in confining, there's the confining pressure relative to atmospheric pressure. and the exponent is 0.32. This exponent of 0.32 is very reasonable for uncemented gravelly soils. If it were cemented, that gray line would go like I'm drawing here. It would be very flat and it would be very high because of the cementation at shallow depths. So it's not cemented. We can prove that to ourselves. The number there at 1 atmosphere represents a large D50, a large C sub U, that is a large uniformity coefficient. So particle spaces are filled in, so between the big particles with smaller particles. And again, as I said, no cementation and representative of normally consolidated soil with no plasticity. That's what we get by just replotting the data like we would have from a lab test. Okay, is it uniform vertically? And the answer is yes, because now you're going to normalize it. Here we normalize it to VS1 at all depths just by using the equation I described to you, but now with the right exponent, very important, and with the right number at 1 atmosphere. And so, yep, it's very uniform, and we're happy. Will it liquefy? Well, this is a chart that Ron Andrus really put together as a PhD student at Texas. And it's mainly sands from Imperial Valley. And here's the earthquake cyclic stress ratio. Here's the stress-corrected shear wave velocity. And you see that it ends at 300 meters per second. And you see that this is a no liquefaction zone, even though we don't necessarily have, the liquefaction characteristics of the other material. When we go back and see what V sub S was in that other material, here we have it. V sub S1 is 380 meters per second. Here's about where 380 meters per second, my red arrow on this chart. No, it's not going to liquefy in an earthquake. You know, when you go to some sites like this and things work out, and if the owner's there and they know about it, the owner seems to want to come and give you a hug or something. And I say, are you wearing a mask? No, that was long ago. We didn't have masks. No, you don't need to thank me. Just pay the bills. And we are very pleased to have been able to help you. So it's nice. Other material quality assessments, that was soil. Here's rock. I'm not going to describe it any more than that, but here's rock. And this is a dam. And when the emergency spillway was used, it failed. And they were able to shut the emergency spillway on these gates and go to another 2 places where they had other gates to help the reservoir. And during the rain, they could get rid of enough of the water so that it didn't overtop the spillways. And we were called in much later to evaluate, 20 years later or so, to evaluate the rock and to evaluate the repair they did. They did a good job. We're very interested in rock. I'm working on trying to do seismic CSD of rock, seismic CQD, seismic SQD, seismic quality designation of rock, and it's going to be on fracturing, and that has effect on attenuation, and we're working hard on that right now. So you can go out and get some very good measurements in rock with this same stuff. That's one of our smaller pieces of equipment we call thumper, but it generates much higher frequencies, and it worked well with hammers on this rock. Okay, second one, nuclear power plants. Here is the Vogtle Electric Power Plant in Georgia, near Augusta, just outside of Augusta, Georgia. They have 2 plants working, and you see 2 new units, units 3 and 4. And the owner, Southern Company, they had a multi-million-dollar, because they had to put in 2 deep excavations and backfill them. They wanted to make sure the backfill would meet their specifications that were used in the design of the power plants that the Nuclear Regulatory Commission, when they applied for the license, They wanted to make sure it met it. And so this was very unusual, but it was very expensive. You know, they had a big investment there. And now, if you want a contractor go crazy, if the contractor has to also interact with the professor, the contractor goes nuts. He said, I'm not listening to that faculty member. But I've heard that before. So we just kept working together. But basically, you see, I divided that fill into 4 layers, and that's what I suggested that we would do. And they're 20 to 25 feet thick, 6 to 7.6 meters. And we'd come in once they got at a certain height, like you see there. So after the first layer was put, we'd test it, second layer, and so forth. Okay, so here they're making the excavation. You see the 2 power plants. Here, the backfill is nearly done. And we were testing, you know, around this area. So you see, we could test the whole area, that even where you see concrete in the nuclear island, where it's going to be, because it's filled high enough up here, and there's a retaining wall. So we did each unit, and you see all the piping and so forth. Wow, it is complex. Here we are on top of it once it's completed. Now we did 4. This is the 4th time we went out there and tested at each new site. And to me, this is beautiful. Let's just look at unit 4. This is unit 4 over here. And so that's the first time we came in. So this is the SASW measurements. And what you see, let's maybe look at this point right here, whatever the depth that is below the top. And when they put the next amount of ground on top of that, of select fill, it moved from there over to that point because of the loading. That's confining pressure. Then the next time it moved over there because of the confining pressure. And the final time it was here. So you see how you could just watch the material behave. And by the second set of measurements, we can say, don't worry, you're going to meet the specifications you have, and I'll show you what the specifications are in a moment. Are the backfills laterally uniform? Okay, you see how these things are also close together? Yes is the answer. And this is a very interesting number. So here is a man-made fill as carefully as possible, and the COV is basically 0.05. I don't think nature can do any better, but nature does some very good things. But that's a very good number to keep in your back pocket if you do stuff like we do, just to see where we fit, and how variable the site might be. Are they vertically uniform? Yes, this one is. The contractor had to pull out some stuff here, and so that was there. Don't worry about it. But when he put it back, he really got it dense. So we made it a little less vertically uniform. It wasn't a big deal. Okay, and I'll tell you another thing about my group up. So here we are. Let's look at unit 4. We're going to take this median profile here in blue. Here it is right over there, just because of the layers that we made it in. But we can fit what would be a resonant column test through it. And you see the slope is the power on the confining pressure. Now this has got silty material in it too. So it's going to be a little lower than 0.25 or 0.26 that you might get for just clean sand. But oh yeah. And so I was asked, well, how well did the lab do? And you know, I didn't answer it correctly, and and they went on to something else. I raised my hand and said, I don't like my answer. And I said that, well, the lab shows more variability, and of course it should, because the sample is this big, that you're testing, and you got huge amount that you're testing in situ. So that little variability that you might find there disappears in the overall scale as long as it's well mixed. Okay, here's what they had to do. They needed to have the shear wave velocity at the base of the nuclear island be at least 1,000, at least 300 meters per second. And this shows you, here's the base of the nuclear island, and here's the 300 meters, and it's above it. Hallelujah. Here we are in this one. There's the 300 meters per second, and it's above it. Everybody was happy, even the contractor that placed the fill. Okay, there's dynamic compaction in Taiwan. That worked very well. We did SASW to do this. This is an interesting one in Italy. That's a landslide from that point to about down here is at least a half a mile. And so nature brought that down in heavy, heavy, heavy rains. And the question is, do they have to excavate this, or is it dense enough that they can just start to build on it? And we, with a big, big bulldozer and so forth, we showed them it was dense enough to build on and not worry about. Extremely cost effective, but you couldn't do it any other way. You could not do it drilling or anything. It's not possible. It was such a hodgepodge. But nature put so much energy into it, it was going to be dense. And yes, we agreed with that. Okay, the deep profiling on the top of Yucca Mountain. Yucca Mountain was meant to be the first geological repository for high-level radioactive waste. Politics got involved and it didn't happen, but we spent about 5 years working on Yucca Mountain. So here's Liquidator on the top of Yucca Mountain, long rays, even had a telescope to help us, total station to help us space things out there and make walking and stretching cables easier. And here we are. This is where the emplacement zone was going to be down here. Though here are on the top of Yucca Mountain, all of those sites. These were on ridges that are heading down. There also were tunnels put in to investigate the material. So here we are in the tunnel. This just shows you it's quite complex. That's an accelerometer. We'd drill a hole, take a nail, pound it in, put a magnet on the end of the accelerometer, whack, it would stick right there. We had a whole crew ahead of us drilling and pounding nails, and we'd be coming behind. So that's the high frequency stuff in the rock, because you're right on the rock. Okay, here's all the data that we had right here. And you can see now the COV at depth is going to be quite high. Always the COV near the surface, almost always, is high. But that's because these stiff layers appeared in some areas and not others. So we divided into two different groups. Here are, down at the title, you see 9 softer sites in group 1, meaning that it didn't pop out here. But there's the tunnel. You keep track of me on time, please. And the tunnel, meaning, is at the repository level. And yes, we did both of those things, so I don't know if you can trust them or not, but there was excellent comparisons. And this is the same thing over where the stiffer sites were, and the same type of material, but obviously geology did something to it and made it stiffer, but that worked out really well. Okay, here's a water tunnel in Washington, D.C. that failed, and we ended up doing that. It's in rock. And you can see my expertise. It's usually with the hammer, and the graduate students get lost, unfortunately, there, but they deserve all the credit. Here is a mine shaft that was going to go, that was connected to a mining operation that had closed, but there was a big open mine at significant depth, and they were thinking of using it as a pneumatic repository. So they pump air into it, have the pressure build up, and then when the power was needed, they'd open up and turn the fans and create pressure out. The wall was fine. They didn't have to do anything to the wall, and we showed that. The last one, am I too far over? The last one, very deep, 500-meter profiling at least. And this is at a greenfield site. That means they want to build a new nuclear reactors there, but they don't exist. Nothing has been done yet. And we did 5 arrays there. Here's Liquidator in normal operation. In normal operation, all the white stuff here and the tires and all of that hold this plate down. And then that weight, which is about 12,000 pounds or something, we excite to generate the forces. And the plate on the plate, and all the white holding the plate down, there are airbags here to isolate the movement of the plate from the truck. It doesn't isolate it, it gives it a good start. And here you see the profiles. This isn't a big site, working out very well, and you see that we're down 300 to 365 meters. Okay, for a long time, I've been fretting over not getting even lower frequencies. And so one night, I think waking up in the middle of the night, I said, okay, I'm gonna lift the whole darn machine up, which is a little bit dangerous. We have to be very careful. And we build a footing for it. Someone does that for us. And now the weight and everything there that's not the stationary parts of the machine are fixed, and we use that to push everything else. So it goes from about 12,000 to 60,000 pounds that we're moving up and down. And that causes us to generate waves. We could only go to 1.3 hertz. This is quite theoretical, but only 1.3 hertz at peak force. Now we can go to 0.65. 2 times 0.65 is 1.3. That doubles the depth that we can go to. If we were going to 3,000, now 300 meters, now we're going to 600 meters. And so we've been using that. I don't have the latest data to show you, but whoops, sorry. But here it is, oops. Here is what you saw in the first one. And this green line, which is a different color in the plot that shows where they are, I'm sorry, is here down extended. And just for your edification, there's at that site the PS logger, and it's shown right here. And you just see that. That's all I'm going to say. But I can tell you, to drill that hole to 600 meters or thereabouts for the PS logger costs more than all of our work we did at that site. So yeah, I'm not sure it was cost effective, but some people might want to see it. No problem. Conclusion: small strain mechanical properties expressed by VS and Gmax play an important role in geotechnical engineering. Small strain mechanical properties are critical and dynamic and static. And I didn't show you static, but we predict the settlement of footings on sand with shear modulus. And it starts out with Gmax. And it tells you that a 1 foot plate isn't very good at all. Okay. Let's see. Continuing evolution, evolving field testing procedures and numerical analyses with Rayleigh type surface waves and log waves form an important and cost-effective way of evaluating VSBS profiles in all times of geotechnical and structural. We do a lot of structural testing, as you saw in the tunnel and so forth, looking out, do a lot of concrete testing. Under all types of field situations, the importance of this work in modulus measurements and shear wave velocity measurements is only going to continue to grow, because it's theoretically solid and it can move forward. And like I say, when we start doing damping measurements, it's going to really have a huge impact on what we know about the material. Okay, Professors Sitaram, Prakash, and Jaka, I want to thank for organizing this conference and inviting me, but I also need to give them a special thanks for allowing me to present the first ISET Shamshir Prakash Distinguished Lecture. And I know Shamshir Prakash, and we've interacted for decades. I must tell you, if Shamshir is listening, I hope you can also think that this talk all came from Professor Dick Woods, who passed away just about 6 months ago, because he was also a good friend of yours. And I'd like you to feel that some of this came from him. Okay, many funding agencies helped us. Texas graduate students, I would be dead in the water without them. Faculty, technicians, and administrative staff. It takes a big crew to run all of this. And thank you so much for this opportunity. I hope I didn't spend too much time.
No, sir. Thank you very much for a very lucid and informative lecture. Though you are in the middle of the night today. Thank you.
And all of these slides are yours.
Okay,
Nice.
nice.
You can distribute the slides. It's fine with me.
Okay. There are a couple of questions, and it will be a pleasure if you could answer them. This is a question from Mr. Aniket Desai. Do you agree that MASW test is better than SASW for mode separation? If so,
Oh
why
my
did you
God,
use SASW?
no, you don't even have to finish the question. Not a bit. Oh my gosh. I mean, they try to, you don't see them doing any nuclear power plants. You don't see them doing any type of testing like this. Yeah, I'm just gonna have to stop there. So my answer is clear.
I understand. Okay, again from the same person. When the length of the receiver array was kept so large to get such high maximum wavelength, how to ensure that the generated waves are reaching properly at the farthest receiver without attenuation, especially for a high frequency wave?
There's huge attenuation to get to the farthest receiver. There's huge attenuation just like in soils. But you know, looking at the data, if it looks reasonable to you, and you will, so you have to move forward with that as a quality check, but that doesn't mean something couldn't be a problem there. And when you start reducing your data, you look at it. But no, this is just the physics of the problem. We're not doing anything with, you couldn't have that long a wave if you couldn't generate that much energy. The earthquake really outdoes us, and we can't do anything like the earthquake. But no, that's, and okay, let me say one other thing to repeat it. So when we're at the longest spacing, that may take an hour of going through those 100 frequencies, but you're adding them up each one many more times than for short spacing. So it's a long time, plus it's a low frequency, but without that equipment, you could not do it. You could not do it. Yeah, because, well, I guess there'll be other ways, but right now I don't know what those are.
Thank you. Thank you very much. And I think, these were the questions. So if audience have any other question, please do post your questions. And it's very nice of you that, in the middle of the night, you are able to, help us with your lucid presentation. Thank you very much from the organizers again. So, yeah, I think, we will move over to the next presentation, next keynote lecture.
I don't want to take any of Adrian's time. I hope I didn't, Adrian, take any of your time.
No, sir. No, absolutely fine. Absolutely fine. Okay. Thank you.
But I apologize, Adrian, because I'm about to go to bed.
Have a good night, Ken.
Thank you, sir.
Okay.
A very fine fellow you have there.
Just maybe one question can I ask, sir?
Professor Jekka wants to, please, Professor Jekka.
Professor Stokoi, very nice presentation, very interesting. And we are partly we are a little bit working on MSW, and Mr. Aniket Desai, he's the one who is working on it with us. Sir, I have several questions, but I will restrict to one or two quickly. You have tested wave propagation on the embankment dam as well, which is the sloping ground. So what we assume is wave is propagate vertically downwards, but in this case,
no. You saw with my when I was on the slope, I assumed, and that's an assumption, that the waves were going in perpendicular to the slope. So that little road that I said they built, the dozer would be going like this, and our arrays are parallel to the crest, but we're drawing a line that's perpendicular to that road, let's say, into it. and we let the other folks, the other experts, calculate the states of stress along that direction. We did not do that. We used them so that we could try to get the right states of stress. We might screw it up. So I didn't want to do that. But yeah, no, we assumed that you could take a flat surface and you could incline it, but you'd still be making measurements perpendicular to the surface. And you saw the numbers, it certainly looked that that was very reasonable. And given the other information for Professor Idris and Castro and others, there were more. And there were also some geophysicists on the panel. They accepted, they were happy with that data.
Just another last quick question, sir. You have tested landslide as well using SSW. Actually, in case of landslides, usually it is a heterogeneous. It has the boulders, soil, mixture. So whatever you are getting, maybe average velocity, how we can interpret and how we can use it?
Because it tells you that the material between, and so you're right in that we had a big bulldozer. That doesn't mean every place on the line was good for us, because there could be a huge, almost the size of a house, down there that we wouldn't know about. So we would move around to once again QA our data, so to speak. Okay, what it should look like. But even as soon as you start getting longer waves, if you get waves that are 100 meters long, 200 meters long, well, you can't do the house yet, but you still can do big stuff. And that every line didn't work, but enough of them did to allow the other people like Professor Yamakowski, that's who we did it for, very famous person, Leaning Tower of Pisa, so forth, to look at the data and feel comfortable, and that's what they did, and it's worked. I mean, they built what they wanted to on it, and it's been fine.
Thank you, Professor Stokoi.
Okay.
Thanks from organizing committee,
Yeah,
and
thanks.
also kindly joining in the middle of your night. Bye.
Yeah, Dr. Prasad, just a quick one link with Dr. Ravi's question.
Please.
Hello, can you hear me, Professor Stoko?
Yes, I can.
Please.
Thank you so much for this sort of nice discussion and so much of elaboration on the different practical aspects. So my question is slightly linked with Dr. Ravi's question in case of landslide. How we can use that SASW in case of since we know it's a quite heterogeneous in the crown and also in the toe. The compaction is very different if you go by the stratigraphy as well. So in that case, how we can use in terms of the monitoring, you mentioned about the monitoring. So is there any possibility we can use that SASW data for the real-time or near real-time monitoring? Or any example of this? How we can use that data for the real-time or maybe near real-time data monitoring for the landslide?
Now, let me see if I understand the question. Are you trying to look at the situation where failure may be going to occur and you're wanting to detect the failure zone out there, the developing failure zone? Is that your question?
Yes. So that in the critical infrastructure, especially on the highways, if we can predict little bit of early, so
Okay.
that many of the things can be settled. Yeah.
Okay, so by and large, the answer is no. But let me explain why. The answer is we wouldn't see that, because I didn't say this going through, but there's lots I didn't say, because Professor Rodriguez-Merrick has a lot to say, by the way, too. So you would be looking at a softer area. Now it's starting to expand. I mean, it's starting to shear. That's going to make the material softer compared to the other material around it. Okay, we will not detect an inversion. That would be called an inversion, the softer material beneath it. We will not detect an inversion that is smaller than 10% of the depth to the inversion. So if the inversion is at 100 meters down it needs to be at least 10 meters thick, and 20 meters thick would be better. And it won't be. Your failure surface is going to be too narrow, in my opinion. You know, I'm guessing now. But your failure surface is probably going to be so thin that it will not be seen by that testing technique. By
Okay.
surface. Yep.
Thank you.
That would be a wonderful application, but I'm
Yeah.
not living downstream from it, even if I'm running the test. I don't, I'm not going to trust it.
Yeah, similarly, like I was wondering about that MASW, because there are multi-channel, and all these multi-channel can generate different frequencies and depth also, of different wavelength as well. So thank you. Okay,
Very
next
well.
one. Yeah, thank you. I think it's a nice discussion in both the cases, like for Professor Adrian and also Professor Kenneth. So we had two different dimensions we have listened from two experts, and then the first one, Professor Stoke, so he mentioned about like mostly about the shear wave velocity and different methods, how SASW are useful for the practical purposes. So also, I think we have seen at least about 7 to 8 examples from different sites, and also we have got some sort of information on the how it can be practically used, and it's a nice discussion also in the end as a how it can be used for the monitoring system. So with this brief, I'd like to thank both the excellent keynote speaker, and also thanks to the organizer for inviting these excellent speakers, and as well as the nice discussion. Thank you so much.
Thank you very much.
Thank you, Professor S.K. Prasad and Dr. Indrajit Pal. On behalf of organizing committee, we thank you both for nicely conducting this session, and we also thank Professor Adrian and Professor Stokoi for taking out their time in odd times and making presentation. It's really very wonderful and educative. Thank you, one and all. I request Professor Sitaram, Chairman, if he want to say any final concluding remarks.
No, thank you. I think every session I should not come. It's all right. So but first of all, thanks to both the speakers, Kenneth Stokey as well as Adrian, for an excellent lecture, and I really enjoyed, and also very lively discussion. And I started liking this platform so that I know I can do my work also as well as listen to lectures. Thank you so much. Namaskar.
Thank you, one and all. See you all tomorrow morning.
Thank you.
Tomorrow morning,
Bye-bye.
sorry. Tomorrow morning, those who are interested in yoga session will start at 7:15 in the plenary hall. Okay, please join.
Thank you.
Thank you.
Like
Thank you.
And tomorrow evening, 6:30 is the cultural program, which will be a sort of a really a retreat of Indian culture, particularly Bharatanatyam, and also Hindi songs, which is Bollywood. And in addition to that, there are some children also playing some dances and programs. Thank you.
Thank you. Thank you so much.
Thank you.
Okay.
Thank you.
Good night.
Yeah. Thank you, everybody.
Thank you, everyone.
So, Ravi, are we joining on the other link?
Yes.
Yes, sir.
All right, sir.
Yeah, we'll join the other.
Thank you. We will leave and rejoin on the other link. Thank you.